Thank you. All right, so I left you off last time with a promise to get to something really cool today. We're not going to get there. But we will be there all day on Thursday, okay? I just realized I could start it today, but I really don't want to split it up, so we're just going to wait and save it for Thursday, because we've actually got plenty to talk about this evening. Felt like that's hanging. Anyway, okay. So I'm just going to do a couple of flash reminders of what we talked about last time, and these are kind of be seeds for what we're going to do today. And I will say, although we're going to continue with this sort of painful, crappy story, I will end today with a couple of observations of what is to come. Okay, so you will get excited about what I say at the end of the lecture today, even though the first part of the lecture might be a little bit for you. Okay? So you might recall that we took the particle density from non-relativistic physics, which is the number of particles in a volume, and we divide the number of particles by the volume, and that gives us the particle density. The d's are just there to make everything differential. They're not that important. And then what we found is, to relativize this, we actually had to promote the particle density to a density vector. And one way that we defined the density vector was in terms of the rest particle density. So that's taking a volume, okay, where we are at rest with respect to the volume. And so we define the density in this case to be d eta rest, okay, which is again just a dn over dv rest. Okay, and we're taking this as a fixed constant, and we're multiplying it by the force velocity with which we might observe this volume of particles. Okay, so this is true in any frame. The connection of the frame you're in to the rest frame of the box is exactly described by u mu, and then d eta rest is just the parameter that is associated with the rest frame of the box. Okay? But here's the important thing. In order to relativize it, we had to take dn and promote it to a vector. And what I promised you at the end of the last lecture is that in order to extend sorry. Let me give you a different definition. So this is one definition, okay? An equivalent definition, that's what's confusing me. An equivalent definition is to say that the number of particles is the contraction of the particle density vector with the volume, okay? And remember, this is just, the number is the density times the volume. That's all this formula is saying, okay? Number, density, times volume. The only tricky part, and you might or might not remember it, is that in 3 dimensions, a volume doesn't have a normal, okay? However, in 4 dimensions, because, I mean, you know, if you have a volume sitting there, you can't really, there's not an orientation you have to specify in a sense, okay? However, in 4 dimensions, a 3-dimensional volume is a subspace of 4 dimensions, and so you have to talk about its orientation. So the volume is described by a normal vector times the volume itself, and this is contracted with the density vector to create a scalar, which is the number of particles, okay? So both of these roughly contain the same information. And then what we said at the end of the last lecture was, okay, fine. This is for particles, the particle number. What we're going to be interested in is the 4 momentum, because the 4 momentum contains energy and regular spatial momentum. So we want to talk about this as being something times the volume. Okay? And I might as well go ahead and call this mu, for reasons you'll see in a moment. Okay? Now, clearly, Annabelle? No, it's pretty straightforward. This is a scalar. It's a vector contracted with a vector, right?
Yeah.
This is a vector. It's a blank contracted with a dual vector. What is this?
Is it just another vector?
If it's a vector contracted with a dual vector, it'll give me a scalar. But I want it to give me a vector. So what does this need to be?
Tensor.
A tensor, right. In fact, a rank 2 tensor.
Okay.
So what we actually need this to be is something with 2 upper indices. And now look at that story the indices play out. The nu gets summed over, so it disappears from this side. The mu is left over, which agrees with the mu on this side. That's the kind of index notating that is just going to be key in this course. You always want to make sure the indices on the left work with the indices on the right, bearing in mind that anytime an index is repeated, it doesn't have to appear on both sides. Okay? In fact, it usually shouldn't. So now what we're interested in is this guy. And as I finished last time saying, this is the stress energy tensor, which is what we're going to spend most of our time today talking about. So without any further ado, the stress energy tensor. So, so we'll use this expression, so I'll hang on to it for a bit. But let's first organize ourselves with our stress energy tensor. Notice this is a 2-0 tensor. It's got 2 upper indices and no lower indices. And is Danny here? Oh yeah, you're online. Okay.
I'm here. What's up?
No, you're my next questioner, so I'll just pick on you in a minute. Okay, so what I'm going to do now is I'm going to draw something that's painfully obvious. I'm going to just label every element of this. So there's T01, and then I have T01, T02, T03, T10, T20, T30, T11, T12, T13, T21, T22, T23, T31, T32, 233. Screw you guys for not laughing at me. Okay, anyway. All right. Thank you. I appreciate it. All right. So, what we're going to do is we're going to explore the various elements of this tensor to sort of investigate what exactly it is, what it holds, and so forth. And we're going to find it quite convenient to break it up into this block structure. Okay, where we're going to talk about this individually, we'll talk about this guy, and then we'll talk about these. Now, at first, an important observation is that this is symmetric. Okay? So if we can give these an interpretation, these automatically get the same interpretation. Okay? So we really only have to scan and analyze a little over half of this thing. Okay? 10 elements to be precise. Okay, so here's how we do it. Consider a normal vector, which is 1, 0, 0, 0. Okay? Daniel?
Mm-hmm. Yeah.
Okay, you saw the normal vector that I wrote on the board, correct?
Yes.
What do you think is the corresponding element of volume? Well, I'll break it down. In what direction does the normal vector point?
In the dimension question?
Exactly. Okay, so if you're pointing in the time dimension, what are you orthogonal to?
All spatial dimension.
And so what is a volume in space given by? In terms of differential coordinates.
The dx, dy, dz.
Exactamundo. See, this is not hard. Okay? We pick a normal, and we say this is normal to the volume, and then that tells us what the volume is composed of. In this case, dx, dy, dz. All right? Now what we're going to do is we're going to take this expression, which I said will be valuable, and we're simply going to plug in that normal vector. Okay? Now remember, we sum over all of the components because nu is repeated, but the only non-zero component of this vector is the first one, and it's 1. So in this case, we can write dp mu is t mu 0 times 1 times dv. Okay? Are there any questions about that? Again, I would sum over all of the components of n nu, except 3 of them are 0 and only 1 of them is non-zero, and it's 1. So this is t mu 0, n 0, but n 0 is just 1. Okay? All right? So now what we can do is we can take this and we can say, oh, okay. If I take mu to be 0, so this is an equation with one index on each side that's the same. So this is how many different equations, and I'll ask a person this, just to get this out of the way. Paul! Here. Paul, how many different equations does this represent? Got a mu in it. 4, right. It's 4 different values of mu, okay? So we can start by taking mu equals 0, and I'm actually going to write this below it. And then I can pick mu equals, just say 1. Obviously, I can pick 1, 2, or 3, but those are probably all going to mean roughly the same thing. Okay? All right, this guy tells me that t0, 0 is dp0 over dv, where this guy tells me that t10 is dp1 over dv. Okay? Now let's pick another victim. So many victims. Liam. What's P0? Energy? It's the energy, exactly. We're on a hot streak. Liam, what's P1?
Momentum?
It's the x component of the momentum, exactly. Okay? So, and we might as well call that P1, in which case I should have just left it as dP1. But at any rate. So this is going to be the energy density and we might call that rho. And this is going to be the momentum density. And we might call that pi, or pi I, sorry. Okay? Holy crap, we just figured out 4 of the terms in T mu nu. Well, actually 7, if you include the reflection. But we got all 4 of these. So all we have left is this little cluster down here. Okay? So in order to do that, as you might guess, we'll have to consider a different normal vector. And just as an example, we might use 0, 1, 0, 0, though obviously, whatever we get from this is going to be easily extended to what we would get if we put a 1 here and a 1 here, because this is going to be the X version of the story, this would be the Y version, this would be the Z version. Okay? So really and truthfully, all we have to do is we have to figure out the difference between the time version, which is what we just did, and a spatial version, and then the spatial versions just kind of repeat themselves from X to Y to Z. Okay? All right. I would like for Josh, tell me what I write down.
As the normal vector? Or the dv? Oh, dp mu equal t mu. Let's go with 1 dv.
dv. In what direction does this point?
In the time?
It does.
Oh, just in the x, that one.
In the x direction. So if I have a vector that's in the x direction, what three-dimensional volume is it perpendicular to?
dt, dy, dz.
dt, dy, dz. Or dt and an area in the yz plane. Everybody follow that? Any questions about that? Yes?
I guessed t mu 1. Is that correct or?
Yeah, no, that's correct.
Okay.
I mean, it has to match with what we have here.
All right.
But now we play the same game that we played here.
Cool.
Okay? So here we go. We can do the 0th component of this, which is t01. We already know what t01 is. So we don't even need to play this game. Okay? We can do the first component of it, in which case this will be t11 dt dA yz. And then we might try the second component of it, because this is going to give me t21 dt dA yz. Okay? And I can try the third, but the third is just going to be another version of what we get out of here. I can write it down if you really need me to, but you can just repeat this with 2 equals 3. Okay? Now, obviously, these are two unique things, because this involves a t11, which is on the diagonal, and this involves t21, which is off the diagonal. You follow that? So that's the reason why we should analyze both of these. If we did t3, or if we did mu equals 3, that story will play out much like what we get here, because 3 would be t31, which would be off the diagonal, and we expect it to play out the same. Okay? So here we go. T11 is going to be dP1 over dt over dAyz. T21 is going to be dP2 over dt 1 over dAyz. That is just algebraically reordering these to isolate T11 and T21. Okay? Are you ready? You ready? Let me get a vector. I should really call it a winner, not a victim.
It's a victim.
And the winner is Lauren. You are the one who should be able to do this.
So the first one would be pressure, right? Because that's the time derivative of the momentum density, so, or it would be similar to pressure?
It is exactly pressure. Thank you. Yeah, because dP1 dt is the component of the force along the x direction.
Yeah.
And that is divided by the area in the yz direction. Okay, if you're studying the forces which are orthogonal to a surface, the forces divided by the area is pressure. Exactly. Lauren, you're on a roll. What do you think this is?
Excellent question.
You want a phone friend? Or do you want me to draw another winner's card?
You know, someone else should be, should
Okay,
feel
I'll
the
let
same
somebody
joy
else
that
do
I
it.
have for
I'll
that.
let somebody else do it. Although, there are 4 pictures of you on here. And I think technically she's asking for 4 questions at the top, right?
No.
Okay, all right. I didn't ask Josh more than 1 question either. He's got more than 1 picture on his.
I only have 1 picture of myself
Yes.
on there.
Is it just pressure along the y-axis or different axes?
Well, that's the thing. So, let me actually draw a little picture for you here. I'll draw it up here. So imagine that we have an area in space, and that area is what I'm calling dAyz, okay? And the area spans the y and z plane, okay? And then if we take a force, say along some arbitrary direction, whoops, okay, then we can break it up into its components along the z direction, along the y direction, and then along the x direction. Okay? So, I mean, this force is pointing down, that's why the x component is in the negative x direction, at any rate. So pressure are the orthogonal components of forces on an area. Is that an orthogonal component of the force? No, it's parallel to the surface. So do you have any idea what name we give to forces along the surface versus perpendicular?
I cannot remember.
Anybody know?
It's stress, isn't it?
It's
Wasn't it like shear?
shear.
Yeah.
It's shear, yeah.
Shear
So this is shear. Okay? So what we have just discovered is what our energy momentum tensor is actually composed of. It is first and foremost composed in this upper left-hand block of the energy density, and then the momentum density, and so too here. And then we have the pressure down the diagonal, and then shear here, and shear here as well. Okay? All right? Now, many of you might have encountered an energy tensor or a momentum tensor in 3 dimensions. This is just a 4-dimensional generalization of that. All right? This is going to play an incredible role in this course. So this is not a simple example I'm giving you just to show you something. No, this is going to play a crucial role in general relativity. So you want to become comfortable with this, and I'm going to show you some more tricks you can do with it as well. But these are the terms and their interpretations. And I'll go ahead and tell you that quite often we assume 0 shear, okay? And then I'll show you how to generate a momentum density in just a minute, okay? So are there any questions about this process before we move on? All right, good. Here we go. So now I want to very quickly show you a bit of a trick. Yeah. And then we'll look at some examples of what the energy momentum tensor looks like. So Now recall from this expression, we can write T mu nu is basically dp mu divided by eta nu dv. Okay, that's just taking this and rearranging it. All right, now, this might lead you to the question, what's that, Flournoy? All right. What is it to divide by a dual vector? And we know that multiplying by vectors makes sense in a certain sense, but dividing by a dual vector seems kind of weird. Okay? In order to give this an interpretation, we're actually going to jump back to this context. So remember, d eta mu is equal to d eta rest times u mu, where d eta rest is just dn over dv rest, and then times u mu. Okay, so it's the number of particles in the rest volume. And then u mu is the 4 vector which connects whatever frame you're observing that thing in to the rest frame of that thing. Okay? Now, oh wait, hold on. So we can take this and we can say, all right, well, this is d n u, or mu, which is dn over eta mu dv. Now, both of those expressions should correspond to the same thing, the number of particles, right? Or sorry, the 4 momentum, the four vector density. Kiana, are you online? Kiana? Okay, pick another one. Sean, by comparing this expression and this expression, what can you set equal to? Well, actually, what can we interpret this as?
Is that the rest volume?
Up close, it's the 1 over the rest volume times
Oh, the 4 vector.
the 4 vector velocity. Okay? So again, this is the normal to a 3 volume, and this volume could be dt, dx, dy, it could be dx, dy, dz, it doesn't matter. This is the rest version of that, and this is the 4 velocity connecting the frame you're actually observing it in to the rest frame. Okay? So now what we can do is we can say, well, T mu nu is dp mu u nu over dv rest. Okay? Because T mu nu is just dp mu divided by eta nu dv, but we just proved that 1 over eta nu dv is u mu over dv rest. So this gives us yet another way to express the energy momentum tensor. Right? Now, I am going to, and we're going to use this extensively in our next few examples. What we're going to talk about now is the case of dust. Okay? Dust is perhaps one of the simplest possible examples of an energy momentum concentration. So we can imagine we've got a bunch of particles in a rest volume. And with respect to that rest volume, there's no net motion of the particles, and the particles aren't even moving. They're just sitting there statically, floating in deep space like dust do. Okay? It is the simplest picture. Now, an interesting scenario is to boost this such that we're boosting from the rest frame to the frame which is moving to the right with a speed dv. We're just putting d's in front of everything, just as differentials. That'll be more important when we're in curved space where things are global. Okay? If we boost to a frame moving to the right, this is going to be an easy one, so don't worry, Andrew. In what direction is the momentum of the particles? Say it again? The x.
The rate.
The momentum of these particles is to the right. So this is the rest frame where they're sitting still, and we're moving to the right with respect to this rest frame. So what direction do we see the particles move? The left, exactly. So to the left, we have dp mu, okay? Which in this case we can write as, let me get myself a little bit more room to write it. We can just write dp mu as the number of particles times each of their masses, so we'll just take them all to be the same mass, so it's just m for all of them, times the form velocity. Okay? Does that make sense? I mean, honestly, like, that is the momentum, the form momentum. But we have many particles, and they're all doing exactly the same thing, so we take that one form momentum and we multiply it by the number of particles, which is dn. And that gives us dp. Yes?
But you said the masses of all the particles put together?
No, this is a mass of each one of them.
Of each one of them?
Yeah, each one of them. Yes?
So if we had multiple particles of different masses, would it be more of a summation of
Yes.
masses?
Yes. But we will rarely, if ever, have to think about that. Okay? So I should say this is a uniform dust where every particle has the same properties. They all have the same mass, they all have the same everything else. But the mass is the only thing that's playing a role here, so it's the only part to worry about. Okay? So again, this is number of particles. This is the mass of one. And this is the form velocity. Of one for all. Okay, because they're all the same. All right? Are we ready? Because now we have a more functional form of this differential form momentum, and we can just stuff it right there. So here we go. T mu nu dust is equal to dp mu u nu over d rest. Okay, that should be obvious. It's just a repetition of what I have up there. And now we're just going to plug in that formula. dn m u mu u nu over dv rest. Okay? Now, dn dv rest, we've already given a name, right? Can anybody tell me what we called it? Anybody? Can any of you read? There's no takers?
I learned reading next year.
Oh, goodness. You guys are killing me. Okay, so we have dn rest times the mass times u mu. Can anyone give me an interpretation of what dn rest times mass is? Joel, what do I get by multiplying the rest density times the mass? Well, yes, but
What do you want?
well, I want to remind you that we're really okay. I mean, all right. So I'll just give it to you. So in this class, mass does not really play a role. It's rather mass as a component of the energy. So it's the rest mass energy. The c squared is gone. We set it to 1. But there should be a c squared in there. In which case you'd call this the rest mass energy density. Okay? So this guy is the rest energy density, which of course just pertains to the mass energy, because that's the only energy you have when you're sitting at rest in terms of kinetic energy. Okay? So we could just as well call this rho times u mu times u nu. All right? Rho is what we call this. Yes?
Should that be a d eta rest, or is that dn rest?
Sorry, d eta, dn, it doesn't really matter.
Okay.
Yeah, d eta. Sorry. Okay, now, well, here's a question. Wait a minute. Yeah. Yeah, I like it. This definition involves two tensors, t mu nu and rho u mu u nu. Since this is a tensor and these are tensors, this equation is true in any frame. It doesn't have to be just in the rest frame. We can evaluate it in the rest frame. So t mu nu dust in the rest frame equals, well, if you're in the rest frame of this system, what is the vector u mu? Let me draw a hero here. Louis. Louis?
Hello.
There you are. Louis, what is the 4 vector that describes the rest frame of a particle? The 4 vector velocity that describes the rest frame of a particle.
That's a good question.
Anybody want to help Louis out? Go for it.
I'd like to phone a friend.
All right.
1000?
Yeah. Okay, you just got it. 1000. Remember the 4 velocity, the spatial components of the 4 velocity are just how fast a thing's moving, the 3-dimensional momentum. If you're at rest with respect to the thing, the 3-dimensional momentum is 0. You still have to evolve with time, so you still have a time component to your velocity in 4 dimensions. You can't help that, okay? But now, all we have to do is take 100 and take this and form this 2-index tensor, because this has got an index mu and nu, okay, where we just take various values of mu and nu, and we build this tensor up. Well, there's only one value of mu and nu, which is going to be non-zero, and that's mu equals 0 and nu equals 0. So this is going to be rho. That's it. Pretty cool. I mean, does everybody understand what I just did with this? Forming this into a matrix? You can make this a matrix because it's got two indices. Okay? And so for the 0, 0 term, you take the 0 component of this and the 0 component of this. They both happen to be 1. And you multiply them together. For the 0, 1 component, you take the 0 component of this and the 1 component of this, but the 1 component of this is 0, so it's 0. And so forth and so on for all the rest of the matrix. Okay? So there you go. For a dust at rest, the energy momentum tensor only has the energy density, and it's the mass density, in fact. Okay? Now you know we gotta step it up. We can't just do a dust. Dust is kind of like boring. So we're gonna pull this up to a perfect fluid. So in the perfect fluid scenario, we will get a very powerful result. I know I'm going to regret having erased all that, but that's fine. So for the perfect fluid, what we have is, in this case, a collection of particles, each of which are moving randomly. Okay? And we're going to start the story in the rest frame. So that is, the particles are all moving randomly, but there's no overall motion of the particles. Okay? So that's how we're going to define the rest frame in this case. In this case, defining the rest frame was super simple, because the particles were all at rest, so the rest frame is at rest with respect to the particles. Here, though, you can imagine taking the velocity of the center of mass and having that be 0 to define the rest frame. Everything's moving, but if everything's kind of moving and averaging to 0, then you're in the rest frame. Okay? Now, we are going to ignore shear. So, Tij equals 0 when I does not equal j. And we're going to assume isotropy. This, of course, means that T11 is T22, is T33, is P, pressure. Okay? Because remember, the diagonals of the spatial part of the energy momentum tensor are pressure if they're non-zero. So what we have is T mu nu, and its rest frame is rho P, 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 0, 0, because not only are we ignoring shear, but we have no net momentum density. To get a momentum density, you have to get the whole thing moving so that it has an overall momentum, and then you can talk about the density of that momentum. But the overall momentum of this is 0. Okay? Everybody on board? And hopefully the existence of non-zero pressure is somewhat intuitive to you. Okay, because these things are moving around, so they're banging into the walls, and that creates pressure. Okay, here, no pressure, because these things aren't moving. All right? So now, here is the important observation. We can write this as such, but we can also make use of the following expression. T mu nu is rho plus P times U nu plus P times eta mu nu. Write that down. probably the single most important equation I'm going to give you today. So first of all, just to verify in at least one instance that this equation gives us a result that we've already seen, well, let's imagine u mu at rest, well, that's 1, 0, 0, 0. Okay? So T mu nu at rest is rho plus P times 1, 0, 0, 0, 0, 0. That's what I get when I do u mu rest, plus P times minus 1, 1, 1, 1. That's eta mu nu. What do you get? Any takers?
The thing above it.
I can take
We just got it. Sorry. You get this. Everybody see that? Right? The P here is going to cancel with the P there, and you're going to get P's down the rest of the diagonal. Boom, 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 and an energy density left over. Okay? It gets better than that, though. What if you set P to 0? What do you get? You just get the dust. Okay? So this is a rather powerful result. But once again, here's one of the most important observations about it. It's a tensor equation. This is a tensor, that's a tensor, that's a tensor. This equation, although it does reproduce the results for the rest frame, this equation is true in any frame. Okay? So you can boost, you can rotate, you can do whatever the hell you want. There'll be a u vector associated with that, and calculating the right-hand side will give you the corresponding energy momentum tensor for whatever frame you boosted or rotated to. Okay? Now, T mu nu will play the role of J nu, where J nu, in case you don't remember, is the charge and charge current vector, which is the source in electromagnetism. So remember, Maxwell's equations have the electric and the magnetic fields on the left, and then sources on the right. The sources are all parts of this. Einstein's equation for this class will be curvature of the geometry on the left and this on the right. This is going to act as the source in this class. That's why we spent so much time talking about it. All right? Of course, this is a second-rank tensor compared to this, and so you can imagine Einstein's equations are going to be a little bit more complicated than good old Maxwell's vector equations. Okay, so prepare for that. It won't be too bad, but just prepare for it. Okay? But the rough structure is the same. Sources give rise to effects. In electromagnetism, the sources are charges and currents. The effects are electric and magnetic fields. In general relativity, the sources are the energy and momentum tensor, which actually describes their densities. The effects are the curvature of space-time. Okay? Any questions? Okay, all right. So I'm going to wrap it up with just a couple of statements. So first of all, there's something rather interesting that comes from the energy momentum story.
I have a question.
Yeah, go ahead.
What are the components of J mu?
J mu it's the charge and then the current.
So I just can't read it from the board from the
Yeah,
camera.
it's the charge and the current, which are on the right-hand side of the first four of Maxwell's equations.
Thank you.
All right. So now, and this will hopefully give you some anticipation of what is coming next. Well, first of all, let me actually make the following observation. Once we have described relativistic densities, conservation laws are actually quite easy to express. Okay? And now please remember conservation. Does conservation mean something's constant? Who says conservation says something's constant? Who says conservation allows things to change? Well, I say something is constant. I know we don't teach kids in Physics 100 that, but I'm going to show you that it's true. Okay? What you're used to is the idea that you pick a subsystem and the amount in that subsystem can be associated with the flux of stuff out of it. Right? That's a very three-dimensional way of thinking. We live in 4 dimensions now, folks. Get used to it. So let me give you an example. N mu is the number current density. And what this means is that the partial of N mu, partial x mu, equals 0. However, this is a 4-vector thing, and so we can break it down into the derivative of the numbers with respect to time plus the divergence. Okay? We have charge current density given by J mu. dJ mu dx mu equals 0 equals d rho dt plus del dot J. We have T mu here. Energy momentum density. In which case we have dt mu nu dx mu equals 0, which gives rise to a couple of different things, including dt mu d0 dx mu equals 0, which gives me d rho dt, that's the change in energy density, is associated with the divergence of the momentum. And then we have dt mu I dx mu equals 0. And this will play an important role in relativistic fluid dynamics, which we are not going to take up in this course. Okay? So normally when you talk about something being conserved, what you say is, you take this, set it equal to 0, and then you move one of these to the other side. Right? You say the change in the number of particles is given by the flux of particles through the surface. But in 4-dimensional language, you're saying this. Okay? Now, I'm going to, and these are just going to be a spattering of topics, so I'm not really going to follow off any one of them. Next, what I want to do is kind of give you an array of where we've been and where we're going. So let's start with 3D Galilean, and then we'll go to 4D Minkowski, and then we'll finish with 4D curved. And these are all spacetimes. Okay? So first of all, in a 3D Galilean spacetime, the metric is really just the Kronecker delta, or the identity. And that's only with spatial indices. The metric in special relativity is eta mu nu. That's, of course, if you use rectangular coordinates, so tx, y, z, then the metric eta mu nu takes the form -1, 1, 1, 1. And rectangular coordinates are the ones we typically use in special relativity. What can we anticipate in general relativity? Well, not delta, not eta, but rather a metric which depends on position. The metric can often be a non-trivial function of where you are. Okay? Now, some more interesting observations. If the metric is the identity, then the inverse of the identity is the identity. If the metric is eta mu nu, the inverse of that metric is also eta mu nu, component by component. Okay? That's what I'm writing here. Normally I wouldn't write a tensor equation with lower indices on the left and upper indices on the right. What I'm saying here is that the ijth component of the thing on the left is the same as the ijth component on the thing on the right. So don't think of this as a matrix. Think of it as each element is the same as the corresponding element of the other thing. Okay? In general relativity, that will not in general be true. Okay? Because the metric is the identity in 3 dimensions, the components of a dual vector are the same as the components of a vector. There's no reason really to talk about dual vectors versus vectors. Okay? You know that in special relativity, the components of a dual vector are different than the components of a vector. In special relativity, the only difference is that the time-like component has a negative sign compared to the vector. Okay? But you can't imagine that in general relativity this is also not true. And in fact, since the metric in general relativity is a function of where you are, the case of what is the dual vector will depend on where you are as well. Okay? And then last but not least, in Galilean relativity, where there existed this thing called absolute time, and we could parameterize the motion of anything in terms of its evolution with respect to absolute time, it doesn't work for 4 dimensions. Time is relative. So we had to parameterize things in terms of something absolute, and we ended up using the length of the path through space-time, which we just called tau. And that, as you might guess, is exactly the parameterization that we'll use in curved space. Okay? Now, I'm just showing you like the challenges that you're going to face in a curved space compared to a Minkowski space, and especially compared to a Galilean space. But I want to go ahead and give you an indication of where we're going. I said that T mu nu is going to be the source. What is the thing? So remember, sources create effects. And there's an equation that links them. Maxwell's equations tell you how the sources create electric and magnetic fields. Einstein's equations tell you how the energy momentum tensor creates effects which describe the curvature of the geometry. What do you think the unknown on that is? It's the metric. That's going to be the unknown. Okay? So the metric is what we're going to be solving Einstein's equations to find. Okay, so given the energy momentum tensor, we plug it in Einstein's equations, which I haven't even shown you yet. We're going to develop those. But you plug it in Einstein's equations, and then you solve for the unknown metric. Okay? Now, I would like to very quickly pursue a question which confuses a lot of people. And the question might be posed, do we really have to curve space-time? That is, can't we just relativize Newtonian gravity? Remember, general relativity is a generalization of Newtonian gravity. It's not a generalization of special relativity, even though the names sound like it would be. General relativity is a generalization of Newtonian gravity. Well, why can't we just take Newtonian gravity and make it relativistic? Well, first and foremost, you know, if you do Newtonian gravity, you could start with an expression like G12 is G m1 m2 over R1 of t minus R2 of t cubed times R1 of t minus R2 of t. Okay? So there's a full and nasty vector expression for the Newtonian universal gravitational force. However, you will notice in this expression, there's a t. I'm smiling really big, you just can't tell. Okay, here we go. At any rate, yeah, there's a t in there. That won't be relativistic, right? I mean, what the hell's t? T is, I mean, if, in the Newtonian sense, with Galilean relativity, t is absolute, so t is fine. But I mean, these are two different positions. The t's can be very different, okay? So what we discover is that if we try and relativize exactly this, we find, for example, that orbits become unstable. You'll prove this in your homework. Okay? So a lot of things get screwed up if you take this expression and you just assume that the fastest anything can move is the speed of light. The t absolute, which is what you work with this based on, implies that anything can move as fast as it wants. But the moment, remember, Galilean relativity never thought about the speed of light because they just said t is absolute. Einstein said, screw it, the speed of light's the maximum. And he gave up absolute time for that. So if you try and force this on this, you'll find unstable orbits. And again, you'll prove that in your homework. So a naive version of relativistic gravity doesn't work. However, you might remember another force. There is the Coulombic interaction, which takes a hell of a similar form. I mean, all we do is we replace the masses here with charges and g with k. Does this work with special relativity? Yeah, it does. This looks a hell of a lot like this. I say this does not work with special relativity, but this does. What am I leaving out?
Charges rather than masses?
Say it again.
Charges rather than masses?
So this is charges rather than masses, but that's actually not the key thing. Say it again?
Moving charges?
Moving charges.
Is it there? Like that's just one component of the force.
So what you're getting at, which I appreciate, is this is not the entire story by a long stretch. In relativistic electrodynamics, you have way more than just this. You have Leonard-Weikert potentials. Okay? You have retarded potentials. You have an entire complex structure. You have magnetic fields. You have all this shit in the story. And all of that together conspires to make it work under special relativity. For gravity, this is all you got. There's no magnetic gravitational force. Now, you could say, why don't we make a magnetic force of gravity? You can do that. You can actually take all of the extra structure that's in electrodynamics that makes it relativistically invariant, and you can add it by analogy to this gravitational story. Okay? That'll make it relativistically invariant. Unfortunately, it won't be true. Okay? The effects that you have to add are very, very minimal. Okay? And you can imagine that because in order to find the effects, you have to have masses that are big enough to create gravitational forces. But masses that are really, really huge never ever travel even remotely close to the speed of light. So the impacts of those extra things and the gravitational extension of the story are very, very, very tiny. Okay? But there are two big problems which you encounter when you try and relativize gravity in this naive way. Okay? Two problems. Number one, it is still based on M. That is, the force is still rooted in mass. So M equals 0 plays no role. Okay? However, we know that even objects that have no mass can create a gravitational force, or can at least experience a gravitational force. How many of you ever heard of gravitational lensing? That's the bending of light, which is massless, by a gravitational field. You can't get that from a generalization of this, because this hangs so dearly on M. Okay? It doesn't get the predictions right for M not equals 0 either. That is, you might say, well, as long as you apply it to things that have mass, at least it'll do the correct calculations. It won't get you the right answers. And we'll talk about an example of that, okay? So what we're going to do next time is we're going to fix it. It's going to be a very pictorial lecture. Draw lots of pictures in this one. It's going to be fun. Yes. Very few equations, in fact. In fact, what equations I draw are going to be so easy. Okay? But largely, what they will hang on is this identification. That the inertial mass of something is the same as the gravitational mass. Remember, and you might not remember from Physics 1, or wherever you learned introductory physics, you saw mass introduced in two contexts. One was in Newton's second law, where you were introduced to what was technically called the inertial mass. And that inertial mass plays a role even if gravity is not present. If you have a spring attached to a mass in deep space where there's no gravity, you still got to use the inertial mass. Okay? Then later, you were introduced to the gravitational mass. That's the mass that comes into Newton's universal law of gravitation, or near the surface of the Earth, mass times g. Okay? There is no fundamental reason why those two masses have to be the same, but they always are. Einstein thought long and hard about it, and as a result came up with the general theory of relativity. And we'll do that over the next few weeks. We're done.